As long as the suit is intact, pressure will not be an issue. Either the oxygen will run out, or the system, which removes exhaled carbon dioxide, will stop working. Either way, the astronaut will suffocate and continue floating into the emptiness of space. The same micrometeoroids that can devastate space colonies also pose a lethal threat to spacewalks and entire spacecraft. Plus, in low Earth orbit, these rocky little gremlins have company, space junk. And all of these things are racing around at over 22,000 miles an hour. At these speeds, objects that are only a fraction of an inch wide can be deadly.
A micrometeoroid flying through space is a lot like a golf ball flying through the air, with these differences. The micrometeoroid is much, much smaller. And because it travels at hypervelocity, it's far more destructive when it hits. If a micrometeoroid hits your spacesuit, it's going to put a hole in it. You don't have reach or the ability to patch or fix it, unless you've got a fellow astronaut right there. You're going to die. Your air is going to leak out fairly quickly. It's going to gush out. Your blood's going to boil. That's going to be it.
And what causes blood to boil? Well, in space, boiling blood has nothing to do with heat. It's all about the sudden lack of atmospheric pressure.
The idea that blood boils is really a misnomer. The liquid in your body goes from a liquid state to a gaseous state.
There have been many tales about what happens to an unprotected person in outer space. Here's the real story. As the vacuum of space fills the spacewalker's leaking suit, the liquid parts of the tongue and eyes begin to bubble, along with all of the saliva, internal fluids, and blood. As the blood turns to gas, oxygen no longer travels to the brain, or anywhere else. The brain shuts down within about 15 seconds, leaving the victim unconscious. Soon after, the rest of the cells in the body die. Temperature extremes could also play a role, since the sunlit areas of space reach 250 degrees Fahrenheit, and the shaded areas quickly plummet to 250 degrees below zero. And just how big a hole is too big for a spacesuit?
You're really asking a very small amount of material to stop a particle that could be coming in at 7 kilometers per second. You can see the entry hole from the test, and it has many, many layers, ending with what's called the bladder, and this is a pressure retaining layer. That's about a 2 to 3 millimeter hole, a 4 millimeter for an EVA suit on the soft goods. This material would be considered catastrophic.
Luckily, no one in space has ever suffered this fate. Impacts can also cause trouble in sneakier ways. So NASA goes to great lengths to simulate different types of micrometeoroid damage down on Earth. Researchers inside the hypervelocity building of the White Sands Test Facility in New Mexico create impacts using compressed hydrogen gas guns. These guns definitely bring the heat, shooting objects up to 19,000 miles per hour at shuttle and space station parts to assess the damage.
At that velocity, you can get from Los Angeles to New York in about 8 minutes. The testing that we're going to perform today is on an International Space Station handle that the astronauts use on the outside of the space station in order to transverse around the space station safely. Several astronauts have cut their gloves severely. This is a great concern to NASA because when they design the space station, they are very careful to eliminate all sharp edges because you don't want something snagging the astronaut spacesuits and creating a hole and ending a mission.
Technicians mount the handle in the target chamber, place the tiny 1/32 of an inch wide projectile within a holder that will disintegrate once fired, then add gunpowder to the breech.
We take gunpowder and propel a piston which compresses hydrogen gas up to about 100,000 psi. It's that highly compressed gas that accelerates the projectiles from 0 to 19,000 miles per hour. We use 3 different types of cameras. One takes a snapshot, another one takes a film, and the third type is a digital camera which takes 16 frames at 200 million frames per second.
The technicians retreat behind a blast shield and prepare to fire. The chamber is cleared of oxygen and other gases to simulate the vacuum of outer space. Now, the moment of truth. How much damage did this simulated micrometeoroid cause?
Even though it is a small impact, there's enough of a lip with enough structure so that an astronaut could catch their glove on such a lip and cause a tear in their glove.
And if a projectile only 1/32 of an inch wide can cause this type of damage, you won't believe what a larger object can do. At the NASA White Sands Test Facility in New Mexico, researchers load small projectiles into huge guns. The projectiles simulate micrometeoroids and space junk. They slam into spacecraft parts at up to 19,000 miles an hour, creating disasters on Earth to better understand disasters in space. At such incredibly high speeds, a very small object can cause very big trouble.
I'm standing inside of our largest target chamber of our 1-inch gun. The gun is 175 feet long and can launch up to a 3/4 inch size projectile. I'm holding a target that was impacted with a 5/8 inch projectile, and as you can see, this is the entry hole, and it went all the way through the test article. An impact of this size would be a catastrophic event in space.
The only hope the International Space Station crew would have for survival is to put on emergency breathing masks and head to the re-entry capsule. An object less than an inch wide would have forced them to abandon this multi-billion-dollar facility. That type of scenario is the reason why crews are constantly adding extra layers of protection to the outside of the space station. For another type of space collision, we have only ourselves to blame. In 1997, a Russian cosmonaut had trouble guiding an unmanned cargo craft to its docking point with the Mir space station.
Now, we know in aviation that 70% of the accidents are human-related, so it wouldn't surprise you to think that humans have also a big role in accidents and mishaps in space. The Mir collision actually was because a crew member complained that he wasn't trained enough to do the rendezvous, and the ground control team said, well, you have to do it anyway. The hit occurred and it caused a leak in the cabin pressure, so now they started to lose cabin pressure. And then the space station started to tumble because it was like pool balls. One hits another, it causes it to move. So even a minor thing, just the control of a rendezvous and docking could have almost catastrophic consequence.
But the disasters that have happened in space still pale in comparison to the disasters of getting into space and returning. There is a saying that the first 50 miles and the last 50 miles are the most dangerous part of any mission. The 1986 Challenger launch disaster and the 2003 Columbia re-entry tragedy make that clear. But if we're ever going to travel beyond our solar system, we're going to need to move beyond our current rocket technology. One possibility that both thrills and terrifies is known as an antimatter engine. Inside massive particle accelerators, scientists have created minute amounts of antimatter, which is made of atoms that have the opposite charges of normal atoms. So with antimatter, the electrons are positive and the protons are negative. When matter and antimatter come into contact, they annihilate each other, releasing tremendous amounts of energy.
Antimatter engines have a 100% conversion rate of matter into energy. Realize that even an atomic bomb is only 1% efficient. Only 1% of the mass of an atomic bomb is converted to energy. In an antimatter engine, we're talking about nearly 100% of the mass converted into energy, it is, for the next century,